Hello everyone, welcome to Brain Blitz Audios. In this episode of Mind Maps, we will be dealing with current electricity. This is the third chapter in your physics syllabus for grade 12 CBSE. And as we said earlier, we'll be using a mind map to go through this chapter. As you can see, this is very extensive and has a lot of data. Therefore, we'll be trying to explain this by dividing it into 13 sections. Each section deals with a small topic, which is very important in understanding the whole chapter. Let's begin, shall we? So the chapter is current electricity, and we start off by looking at what is electric current. Electric current is the rate of flow of charge through an area. Now, in your earlier chapters, you know that charge is an inherent property of matter, and the flowing of charge is known as electric current. When charge flows in unit time, it is known as current. Therefore, the formula for I, which is electric current, is equal to Q by T. Q stands for charge, T is for time. It is also represented as J bar dot ds bar, which is integrated together. J represents current density. We'll come back to that in a minute. And ds is the differentiated area. So these are the two formulae by which we can determine the amount of electric current flowing in a circuit. Let's move on to current density. Current density is the amount of current flowing in a unit area. So the formula for current density, which is represented as J bar, is equal to delta I divided by delta S cos theta, which is also equal to sigma into E. Delta I refers to current or change in current, and delta S refers to the area of cross section. Theta is the angle between the area vector and current flow, and sigma is a constant known as conductivity, because in this formula we found that current density can also be represented as sigma times E. Now, sigma, which is conductivity, is the reciprocal of resistivity. And this constant, which is known as resistivity, we will be tackling that constant in a later section of this video. So let's move on towards drift velocity. What is drift velocity? In a conductor, the elements are made out of free electrons, free valence electrons, and metal elements, such as positive or negatively charged metal elements, which are positive centers. Now, in a current, in a current carrying conductor which doesn't have any electric field, these electrons go helter-skelter and they move very fast in the terms of 10 raised to 6 meters per second. So they're in the order of 10 raised to 6 meters per second in speed. So, but since they're moving in random directions, their net speed becomes 0. Their net velocity becomes 0. However, when we start applying an electric field on the current carrying conductor, all of these electrons will start moving in one direction only. And that is actually opposite to the current carrying conductor. If I draw another diagram and I find the field moving this way, then the electrons start moving this way. So this is the situation where drift velocity is calculated. The formula for drift velocity is Vd is equal to I divided by NEA, which is equal to J divided by NE. Now, what are these values here? Vd stands for drift velocity. I stands for current. And the value NE, if you've studied in your previous chapter, would be the same as that of Q. And Q is charge. N is the number of electrons present in the conductor, and E is the charge of one electron, which is 1.6 into 10 raised to minus 19 coulombs. And A is the area of cross-section of the conductor in question. Now, we know that current density J is equal to I divided by A, which is current divided by area. So using that, we will get the formula for drift velocity as J divided by NE, where J again stands for current density and NE is the same value as before. N stands for the number of electrons and E stands for 1.6 into 10 raised to minus 19 coulombs. So that gives us the total charge present in the conductor. Let's move on to a quantity known as mobility. Mobility is the measure of the drift velocity divided by the electric field acting on the current carrying conductor. Therefore, the formula for mobility, which is represented as mu, is Vd divided by E, where Vd stands for drift velocity and E stands for the electric field. Now, we find another formula here, E tau divided by m. You should know that drift velocity is also expressed as minus E tau divided by m. So when we divide drift velocity by E, the E on the formula of drift velocity gets cancelled. So we get the formula E tau divided by m. Now E stands for the charge on one electron, which, as we've seen earlier, is 1.6 into 10 raised to minus 19 coulombs. What is tau? Tau here is referred to as the average collision time. The reason for that is, in a conductor, we do not exactly know which electron hits which positive center. So it can go here and hit this one, or it can hit this one and then rebound itself with the same speed as before. The time measured can vary. So when we take time in the formula for mobility, we take the average collision time. So we take out all the collision times present in the conductor and we divide by the number of collisions taking place. So it becomes an average. So tau is the average collision time, also known as relaxation time. So that is the value of tau. And this value of tau is important in calculating mobility and drift velocity. Now we move on to a very important part of this chapter, which is known as Ohm's Law. A scientist named Ohm put forth the statement that potential difference of a present across the ends of a current carrying conductor is directly proportional to the current flowing through the conductor. When we take V as the potential difference across a conductor and I as the current, we get the relation V is proportional to I. That is, potential difference is directly proportional to current. To make this into an equation, we use a constant of proportionality, which is R. So we get the very famous formula, V is equal to IR. V stands for potential difference, I stands for current, while R is a constant of proportionality known as resistance. Now, this refers to the opposing of the movement of electrons in a conductor. That value is known as resistance. Ohm's law can also be thought of as J is equal to sigma E, where J is current density, sigma is conductivity, and E stands for electric field. But for most of the chapter, we'll be taking this formula, V is equal to IR. Let's move on to learning about resistance. We know that resistance is the proportionality constant present in a conductor, where a current is flowing through a potential difference V. Resistance, however, can vary according to some factors, and we can analyze them by analyzing the formula for resistance. R is given as rho L divided by A tau. So let's look at our variables. Resistance is directly proportional to the length of the conductor in question, and it is also inversely proportional to the area of the conductor in question. So the longer the conductor, the more the resistance, and the wider the conductor, the less resistance it develops. Now, we get the relation resistance is proportional to length divided by area. In order to get this into a formula, we use another proportionality constant, which is rho L by A. And this rho was the resistivity we were talking of earlier. This is the amount of resistance present in a conductor of unit length and unit area of cross section. And the value of resistivity would change according to the nature of the conductor or what the conductor is made of. Now, in our formula, we find there's the use of tau or relaxation time. In usual parlance, the value of tau is equated to 1. So the general formula that we'll be using is R is equal to rho L by A. Now, how do you find the resistivity of a conductor? We've seen in the earlier part of this video that resistivity is inversely equal to conductivity, or resistivity is the reciprocal of conductivity, or which is represented as sigma. So we write resistivity as 1 by conductivity, and its unit is ohm meters. We can also write sigma, which is conductivity, as the reciprocal of resistivity. So sigma becomes 1 by rho. But according to our formula on Ohm's law, J is equal to sigma E, we can calculate sigma or conductivity as J divided by E. And that's the formula given here for conductivity. In most of the circuits in daily life, we don't usually have the setup of a unique voltage, a unique current, and a unique resistor. In most of circuits in daily life, we have hundreds of resistors grouped together in various arrangements. So in grouping of resistors, we will be learning about two main types of grouping: series grouping and parallel grouping. In series grouping, two resistors are connected to each other in series. That means the end of one of the resistor is attached to the beginning of the other resistor. That means that both of these are connected in series. Now, in a series connection, the amount of current, that's I, flowing through the initial resistor is equal to the amount of current I flowing through the second resistor. So therefore, the value of I is constant. If we use Ohm's law, we know that V is equal to IR. Now let's keep this as R equivalent to find some formula. So let IR equivalent be the voltage present through a range of resistors, say IR1 plus IR2. And let's take the left side as IR equivalent. Now here, the current is constant, so it's taken out of the equation, which leads us to the equation R is equal to R1 plus R2 for two resistors. And for an arrangement of n resistors in series, we write R equivalent is equal to R1 plus R2 plus R3 plus etc. until plus Rn. So we take the sum of n resistors to find the equivalent resistance of a series connection. Let's move on to the second type of resistance grouping, which is known as parallel connections. Now in parallel connections, both ends of two resistors meet at common points like this. In this arrangement, the resistors are said to be in parallel grouping. Potential difference across any 2 points in a circuit is the same. So in parallel grouping, the potential difference always is constant. So to find I equivalent, we will be summing up two currents, I1 and I2, and we use Ohm's law here. So I equivalent becomes V by R equivalent, which becomes V by R1 plus V by R2. Again, the voltage or potential difference is constant here, so we take it out of the equation, which leads us to this. R equivalent is equal to R1 R2 divided by R1 plus R2, or more simply, 1 by R1 plus 1 by R2. And this is for two resistors. Suppose we have n resistors connected parallelly. So the equation becomes 1 by R equivalent becomes 1 by R1 plus 1 by R2 up to 1 by Rn. So here we find out the reciprocal of the equivalent resistance, and then we flip it over to get the equivalent resistance. So that's how we calculate the value of resistance in a parallel grouping of resistors. Let's move on to the next topic. Temperature dependence of resistance. You know that R is equal to rho L by A, and this value rho is dependent on the material of the conductor. Therefore, it's always constant for a given conductor of same material. However, the values of length, and area can change with respect to temperature. So resistance has a relation with its temperature. And the formula is given by R is equal to R naught, and then in closed brackets, 1 plus alpha into T minus T naught. How do you recognize quantities here? R is given as the resistance at temperature T, and R naught is given as resistance at temperature T naught. T is the final temperature, and T naught is the initial temperature. And alpha is given as the coefficient of resistivity, which always stays constant. To find resistivity, we integrate the value of 1 plus alpha into T minus T naught. So the integration of this value gives us the resistivity of a current carrying conductor. Let's move on to another important part of this chapter, and that is this part, the electric cell, is the source of potential. Electric potential is generated by an electric cell. Let's look at what it is. It is a device which maintains a potential difference between its two terminals. And it's represented diagrammatically like this. And when you have two or more connections, two or more electric cells grouped together, you get a battery. In electric cells, there is we know that an electric cell produces a voltage across a current carrying circuit. But do you know that the cell itself also has a sort of potential difference? That potential difference is known as the EMF. Let's look at the definition. It's equal to the potential difference between the terminals of this cell in a circuit which is open. That means the switch has not been turned on, it's turned off, and then in a circuit where the switch is turned on, turned off, you can find the EMF of an electric cell. So this is the force which is present between the positive and negative terminals of a battery. So this quantity here helps us to find the EMF. Now, note here that EMF stands for electromotive force, but it is not force. It is potential difference. The misunderstanding probably occurred in the early ages of electricity when this quantity was not fully understood. Let's find the electromotive force present on an electric cell. We represent it by E, which is equal to W divided by Q. W stands for work, Q stands for charge, F stands for force, and D stands for distance. And this quantity distance is the distance between the terminals A and B. We know that current passes through an electric cell, and it also has a potential difference inside it known as the EMF. When there is potential difference and current, there is always resistance. Therefore, the next thing that we'll be studying is internal resistance. This is the amount of resistance exerted inside an electric cell when a current carrying conductor flows through it. And the formula here is given as VA minus VB is equal to E minus IR, which quite simply states that VA minus VB, which is the potential difference, is equal to E, which is the potential difference inside the cell, minus IR, where I refers to the current and R refers to the internal resistance of the cell. Using this formula, we'll be able to calculate the internal resistance of a cell. Another formula which can be derived out of this is I is equal to E divided by R plus R. I stands for current, E stands for the EMF inside a cell, and the capital R stands for resistance in the circuit, like this one, and the small r stands for internal resistance. Let's move on to grouping of cells. Since electric cells have resistances, they are also grouped in series and parallel combinations. In a series combination, we know the formula I is equal to E by R plus R. Now suppose you have two cells connected in series. Therefore, they would have two values of E, E1 and E2, two values of internal resistance, R1 and R2, So therefore, we'll get the formula E1 plus E2 divided by R plus R1 plus R2. Okay? And so we can calculate it as E1 plus E2, which is the sum of the EMFs, as E naught and plus R naught, which is the sum of the internal resistances of both the electric cells. So when we compare these two equations, we will get the total EMF of the combination as the sum of the respective EMFs of the cells. And the internal resistances, the total internal resistance will be equal to the sum of the internal resistances of both electric cells. This is series grouping. And that's when both the batteries are in series. What happens when both the batteries are in parallel? In this situation, we get the formula E equivalent is equal to E1 by R1 plus E2 by R2. And when you simplify it further, you get this formula, E1 R2 plus E2 R1 divided by R1 plus R2. And this is taken out of the formula for I, which is E equivalent, that is E1 by R1 plus E2 by R2, divided by R plus the combination of internal resistances. And if you've learned the previous segment, which talked about resistances in parallel combination, you would know that it would be R1 R2 divided by R1 plus R2, arising from the formula 1 by R1 plus 1 by R2. So the equivalent internal resistance of a combination of electric cells parallelly will be equal to 1 by R1 plus 1 by R2, which is the reciprocal. 1 by R naught is equal to 1 by R1 plus 1 by R2. Now, we've so far studied about electric current, current density, Ohm's law, resistances, resistivity, conductivity, and many other terms which are related to Ohm's law. But did you know that Ohm's law is not perfect? Ohm's law has a very big problem. It cannot handle a lot of circuits joining together at a single point, like this. Therefore, another scientist known as Kirchhoff developed a couple of laws for electric circuits. The first of these laws is known as junction law. Now, the statement here says that the algebraic sum of all the currents directed towards a point or junction is 0. That means sigma I at the point P, sigma of the currents at the point P will be equal to 0. Let's look at the situation. So let's try to recreate that diagram present. Okay, so we have an I1, an I2, an I4, an I3, an I5. So here we find that these three currents, I1, I2, and I4, enter into the circuit, into the junction, and these I3 and I5 move out of the junction. So what the first law states is that the sum of the currents entering a junction, which is I1 plus I2 plus I4, would be equal to the sum of the currents leaving the junction, which is I3 plus I5. No current is wasted. This is the first Kirchhoffs law, which is known as junction law. Let's look at the second law, which is known as the loop law, or otherwise mesh law. It states the algebraic sum of all the potential difference along a closed loop is 0. Let's draw a circuit. Okay, so this is a cell with EMF E and a current I flows through it from the positive end to the negative end, and we have a resistor R as well. So the mesh law states that the algebraic sum of all the potential difference across a closed loop is 0. There are two types of potential differences here. One is the EMF E, and the other is V, which is calculated as IR. So according to Kirchhoffs' second law, sigma IR, which is the sum of all the products of current and resistance, would be equal to sigma E, which is the sum of all the EMFs of the combination. And in accordance with this statement, it would mean that sigma IR minus sigma E would be equal to 0. Okay, so which means that the product of current and resistance, which is the potential difference across the circuit, would be equal to the EMF of the electric cell. This is Kirchhoff's second law, which is known as mesh law or loop law. From now onwards, we'll be looking at some of the devices which uses Kirchhoff's laws. The first one of these is a Wheatstone bridge. This is a combination of resistors, and over here we try to find a fundamental principle known as the Wheatstone's principle. Now, to get the Wheatstone's principle, we will first apply Kirchhoff's mesh law in the given circuit ACD. Then we apply it on another loop, which is BDC. So we apply it independently, and then we get the formula R1 divided by R2 is equal to R3 divided by R4. Notice that there is a galvanometer between C and D, but the fact is that this galvanometer does not have any current flowing through it, because in a Wheatstone bridge, R1 is always equal to R3 and R2 is always equal to R4. So the principle of Wheatstone states that resistances are balanced by the following formula. R1 divided by R2 is equal to R3 divided by R4 on a setup known as a Wheatstone bridge. This means that the potential difference at C will be equal to the potential difference at D. And since the potential differences are the same, there is equipotential across the central line. The central wire will not have any current flowing through it as there is no potential difference. So the galvanometer will not have any current flowing through it. In the next device, which we know as the meter bridge, we find the unknown resistance using a setup. So we have a 1 meter length wire. We have an unknown resistance X and a known resistance R. And we also have a device known as a JEE. Now this device is placed on the 1 meter long wire, and it also has a galvanometer attached to it. This is the JEE J. Upon moving the JEE, there comes a length L where the value on the galvanometer is 0. This is known as the balancing length. And in a meter bridge, the fundamental principle that we arrive at is that S by R is equal to 100 minus L divided by L. Now suppose L is this length. The remaining length on the wire, which is 100 centimeters long, would be 100 minus L. So we need to find both lengths on both sides of the point where the jockey makes contact with the wire. And that will be equal to the unknown resistance divided by the known resistance. So we'll find the unknown resistance using the formula S is equal to R into 100 minus L divided by L. Let's move on to the last device and the last part of this chapter, known as the potentiometer. A potentiometer is used to find out the potential difference across a certain length of wire L. And the formula to find the potential is VA minus VB, which is potential difference, divided by L, which is the length of the wire. Now, there are two experiments which helps us to find out two different quantities using a potentiometer. The first is the comparison of EMF. Using Kirchhoffs law, we will get the formula for comparison of EMF as E1 by E2 is equal to L1 by L2. Now, E1 would be equal to the first EMF of the cell, and E2 will be equal to the second EMF of the second cell. L1 would be the balancing length present when the electric cell of EMF E1 was present, and L2 would refer to the balancing length of the circuit when the electric cell E2 was present. So E1 by E2 would be the same as L1 by L2. This gives us the relation E is proportional to L. The next formula helps us to find the internal resistance of a electric cell. So we use two relations here. E is proportional to L, which is used for comparison of EMFs, and ER divided by R plus R proportional to R2 to get at the formula for internal resistance as R, which is the resistance of the resistor in a circuit, and then inside bracket we would write L1 by L2 minus 1. L1 is initial balancing length and L2 is the final balancing length. These are also known as lengths of null point. Null point refers to the galvanometer approaching 0. And so we've completed the chapter current electricity. This chapter is very important, and I hope that this video helped you guys to understand it a lot better. It's very helpful for revising in last-minute preparations for examinations. Did you know that Brain Blitz Audios provides free education to all through YouTube? To be a part of our journey, please subscribe to our channel. Thank you for watching this video. See you soon. Until next time. Bye-bye.